right, can everyone hear me? Hi everyone, I'm Nada Amin. I work with Martin Uderski at EPFL, and one of the projects is this dot calculus. Dot stands for dependent object types, and it's a core calculus for path-dependent types. So we're developing it to have a core understanding of these path-dependent types in isolation, but it's also a good core calculus to disfigure Scala into, the Scala type system. So Martin is developing a new compiler called Dotty, which uses dot as its core type system. And another thing I will show here is that dot has extra constructs which simplify type inference in Scala. And finally, I'll give some idea of how to prove dot is type safe by showing some challenges in the meta theory. But to get started, I just want to relate types in Scala to types in dot. So in Scala, you have a lot of different ways a lot of different concepts for your types. And I guess we can group them into two categories. On the one hand, there's these modular or object-oriented features, such as just having a named type, or a compound type where you take two traits and mix them together. And the refined type where you start with some base type, here channel for example, and you add some new methods or refine some pre-existing methods with more precise types. On the other hand, there's all these parametric way to construct types that I'm calling functional. So for example, you can have a list of string. And well, if you have a list of string, then what is list by itself? So you can think of list as something that takes a type, such as string, and then return this parameterized type, list of string. So list by itself is not, we would call it a higher kinded type, because it's something that takes a type and return a type. And then I also have this existential type where I say, well, okay, list of t for some t, but I don't know anything about it. So the question is, if we can reduce the number of core concepts, then that would be a simplification in the language. Right now, there are these modular and functional categories for doing types, and could we reduce one to the other? So the key idea here is we could reduce the functional to the modular by relying on type members for these parameterized types. So for example, if I have a class list, which has this LM type parameter, then I can turn it into a class list which has no type parameter but has an abstract type member LM. And then when you have a parameterized type, such as list of string, well, it's the same as just refining this LM type member to string. And then the question becomes, what about existential types and higher kinded types? Well, here the idea is that for an existential type, list of something where we don't know anything, it's pretty similar to just having this list with this abstract type member LM, because we don't know anything about this type member. And for higher kinded types, we kind of make the same bet by saying, well, if you just have, so this one is a bit strange, because here this, the higher kinded type list was taking a type and returning a type, and here we're saying this list is fine by itself. You can refine it later, but if you leave it just as this list, it still means something in the language. So it means a list where the type member element is fully abstract. So clearly something is strange here, because we've reduced existential types and higher kinded types to the same thing, but hopefully this will actually be a useful simplification. And in the current versions of the disfiguring, we do something a bit more complicated to keep the full power of higher kinded types, but that's really the basic idea, changing type parameters to type members. And so the idea then is that we can just, at least at the core level, reason about just named types, compound types, and refined types. And the key enabler for this is to have these abstract type members. Okay. So one advantage here is that you get at least some conciseness. So before, if you wanted to mix a hash map with a synchronized map, you had to specify twice what the type parameters were. But in this new scheme, what happens is that when you mix two things, the most specific declaration actually wins, or at least we mix them to create the most specific one. So here, if you say, well, I have a new hash map where the keys are string and the values are list of int, then that will also be understood that when you mix these two things, this is what will win, because in synchronized map, everything is still abstract. Okay, and just to give a more motivation why type members are useful, one common pattern you might have is and this has been known in the standard ML community for a long time, is you want to have two components that refer to some parts of each other, but you don't want to hard code those references. So let's say you have a trait symbols which define all the symbols for, you can imagine that this would be part of a compiler where you would have symbols and types. So within symbols, we have this abstract type member for types, and we can refer to it. And then similarly, in the types component, we have this abstract type member for symbol, and we can refer to it here by saying that each type has a symbol. And then it's only when we put the cake together that all these abstract type members become instantiated with the most precise definition. As another example, it's very common in the functional programming community to define these modules which have these type members that represent some functionality abstractly. So this is, for example, taken from a paper on functional data structures by Okazaki and others. And what we see here is that we're saying, okay, this heap module just defines the interface of and all these operations on heaps and elements. So we just have an abstract type heap, an abstract type element, and then we define all these operations such as, is the heap empty, can you insert, inserting an element into a heap to get a new heap, and so on. And then you can create an actual implementation of this by specifying what your heap type is. And so the one reason why this is useful is that compared to a usual object-oriented implementation where you would have a sort of asymmetry between what is the this element and then what is a parameter, here it's completely symmetric. So say I have two modules that are left abstract. So I have a heap module M1 and a heap module M2, and then I can try to use the merge method of the heap module N1 to merge these two heaps. Well, by default, Scala will complain because these heaps are treated as different abstractions for the same interface. So you cannot really mix an M2 heap with an M1 heap because they might have different implementations that are incompatible. And if you wanted to mix them partially, well, you can use subtyping to reveal some parts of your implementation. So the idea here is that we use the common notion from object-oriented programming, subtyping. By adding this type member, we add a notion that allows us to do these abstract data types. And so we're kind of mixing ideas from the object-oriented community with the functional programming community in terms of how they deal with modules. Okay, so now I just want to summarize the types as we have them in dot. So the key thing we want to capture is these path-dependent types, so p.l. And the idea here is that you can have a refinement type where you give a declaration, and you have the usual method declaration and field declaration, but in addition you have this type declaration which says that you have a type L that is lower bounded by S and upper bounded by u. So in the examples we saw where I said like type LM equals string, that just means that the lower bound and the upper bound are the same. So in which case you could just type L equals another type. And so once we have these type declarations, we need a way to refer to them as types, so that's what p.l allows you to do. If you have a type which has a type member L, then you can do p.l to refer to it. And we also have this top and bottom, which is really like any gives you no information, and nothing is usually something you can only get if you have looped. So it's not really, it should not be possible to get nothing at runtime. So it's the top and bottom of your lattice. And finally, this intersection and union are the new constructs of dot. So so in Scala, you have this with, like you can say a channel with logging, for example. And this intersection behaves differently from with because it's symmetric. And what we wanted to capture with these intersection and union was really a way to just say, well, if you have two types, I want to know what is their least upper bound, and that would be the union, and then their greatest lower bound would be the intersection. And so why is this? Why is it useful to add these two features? So the main motivation was type inference in Scala. And just to give a concrete example, say you have an if statement, then Scala has to infer what the type of this O is by looking at the types of the then branch and the else branch. So it's trying to find the least upper bound of these two types here. The types of these two expressions here. And so here I'm creating a bit of a convoluted example, but it's just to show that the engine might work pretty hard, because what we have here is that, so we have this trait C and this trait D, and if you try to take their least upper bound, which means like a type that represents both what C and D have in common, then what happens is that for the type member T, you can be as specific as you want. So you can say, okay, well, it's A with B, right? They both have A with B. And then for the type member T, it's upper bounded by A with B again. And then for this type member T, you can keep going like this. And if you ask Scala, it will just give you an arbitrary truncation of this type. So here it just said, okay, I computed that T is upper bounded by A with B. But then manually, you could actually go further. So here I manually asked if this if expression has this type, and Scala accepts it. And the type here is more precise than the one inferred from Scala. So somehow, the type inference in Scala, to be robust, it should always infer the least upper bound, but then if it did that, then it wouldn't be able to do anything in that case, because the least upper bound, you would need like it's just represented by this infinite sequence, so you would need you couldn't even type it in the repo. Okay, so does this matter in practice? And do we actually, is it important? Well, so from an abstract point of view, it is a bit brittle, right? That you don't really know how it will infer this type. But in practice, it's actually even worse, because, well, this is only the first few characters of an example where it's trying to infer this least upper bound, and it goes on for more than 20,000 characters. And I took this from a bug report, where what happens is that you have a mutable map where the values are mutable sets. And I mean, this is the gist of what happens in one branch of the if the map does not contain the key, then it adds the key to the map. So this plus equal expression here returns a mutable map. And in the other branch, it just updates the value set with a new element. So here what we're returning is a mutable set. So when you have this expression, Scala is trying to infer the common type, the least upper bound between a mutable map and a mutable set. And these two things, these two types have a lot of operations in common, so it works really hard to give this complicated type. And actually, in this case, it doesn't even matter because we're only using the if as a statement for side effect. So somehow it worked very hard to compute this type, and then we don't even need it. And this was, in this bug report, the problem was that this was really slow for the compiler. And this 20,000 characters that you get is actually after the bug fix. And so it was actually doing it pretty quickly, but it was this humongous type. And of course, one issue is that you might get such a type in your error message if you end up trying to do an operation on the result of this. Okay, so in .t, this is actually much more manageable because just by using these intersection and union that we have in the core calculus, we are able to, whenever the type inference engine needs to compute, say, a least upper bound, it just takes the union without having to really compute what's in there until it needs to. So in some sense, we are making this lazy by delaying we don't construct a type when we don't need to. We just say, okay, we will use this union from the dot core calculus, and then if we need to dig a little bit deeper in this type, then maybe we will look at what methods it actually has. Okay, so now I just want to give you a sense of the challenge in the meta theory. So how do we prove that that a calculus like dot is sound, and what does it mean? What does it mean? So the main thing we want to show is that well-typed programs can't go wrong. So here I'm using JavaScript, for example. So in JavaScript, if you take if you do like a field selection on an object on undefined, then you get this type error: cannot read property bool of undefined. And then if you call something that is not a function, you also get a type error. So intuitively, these are the things we want to catch. In Scala, it's not possible to, if you do a field selection, then you know statically that this field exists, so you wouldn't get such a type error at runtime. And similarly, if you call a method on an object, then this method should exist at runtime. Okay, so this is a crash course on how you prove such things using this syntactic approach. So the idea is that you start with a small step operational semantics of your calculus. So here I haven't even shown too much the term language, but the idea is that you would show all your steps. So if you have like a path such as a.b.l, you would show where this a.b reduces to something, let's say O, and then you have o.l, and you show each step of how you go from a complex expression to a simple expression. And at the end, once you finish all these steps, you either get a value, something that makes sense on its own. So for example, you might, in the context of this calculus, you might have just say an object, and which refer to something in the heap. Or then if something goes wrong, you would get a stuck term. So for example, O.L, and this O object doesn't have a field L, so you cannot proceed with the computation. And then the usual way to prove type safety is through these progress and preservation theorems. So progress says that if a term type checks, then it can take a step or it is a value, but it is not stuck. And then preservation, the preservation theorem says if a term type checks and steps, then the new term also type checks with the same type or subtype. So the idea is that if you have a complex expression, then by applying progress, you know that it can take a step or it's a value, and then by applying preservation, you can iterate and say, okay, well, I know that the new term type checks, and I can apply progress again and preservation. So by putting these two things together, we can prove type safety, and it's nice to have them divided in this way for the purpose of the proof. And really, in our context, preservation is very tricky, and that's what I want to show a little bit. So the reason it's tricky is that we have these paths that are something at runtime, right? And at runtime, we might have more precise information about these paths, and we might have reductions involving these paths, and somehow we have to relate all of these things in order to prove preservation. So just to give a simple, an example where one intuition is that, like if you want to think of preservation intuitively, you can think of it, okay, does inlining preserve my types? That's a simple proxy for it, but it's not quite exact. So here the idea is that we have this method ID, which is really just implemented as the identity function here. And if you just look at the trait abstractly, we have an abstract type member name, and then this ID function takes anything to a name. So here I have a string, and by invoking brand ID on it, I get a brand name. But then if you looked at the implementation of this method, it was really just the identity function. And on the other hand, hi as a string is not a brand name. So that's a pretty tricky situation, because it means that if we were showing all the steps, we would in the proof go from this brand.id, which takes hi, to hi, and then we would have to say, well, the type is the same, but at the top level, hi is not a brand name. And in fact, it wouldn't be sound to just always think of it as, okay, we can ignore what this type is, because, well, if you just look at the type abstractly, that might be all the information you have. You just know that this brand has this type here with this abstract type member, and if I implemented it differently, then here it wouldn't be sound to say that what I get out of this method is also a brand name, because here I implemented it just returning integers. So I mean, this just shows that you can't always, there is something subtle going on in terms of like trying to show all the steps, and always having these intermediate objects that you have to type. And so now I just want to give a flavor also for how do you subtype these path-dependent types. So the idea is that if you have a path-dependent type PL, and you want to know whether S is a subtype of PL, then what you do is that you look at the lower bound, and you try to see if S is a subtype of the lower bound. And similarly, if you have the path-dependent type is on the left, then this time you look at the upper bound. So just think of it as the path-dependent type. When we declared the actual type member, we lower bounded it by a type, and we upper bounded it by a type, and we used the lower bound to when the path-dependent type is on the right of a subtyping relationship, and the upper bound when it's on the left. So it kind of gives you this range in which your type is abstract. And just to give the intuition here, when P.L is fully abstract, then that means that you can't, so the lower bound is nothing and the upper bound is any. That means you can't really open it on the right, because here you would have to say that S is a subtype of nothing, and that you can't show unless S is nothing. And then similarly, you would have to show that any is a subtype of U. So also you restrict your type. So that means that when the type is fully abstract, you can't really involve it with other types unless you actually have a p.l within here. So yeah, and then one thing that happens is that you have these issues when you're trying to relate two types that that look different superficially, but when you have the runtime information, you realize they're the same. So here the idea is that A has a field I, which is equal to B1. And A has this type upper A, and I has this type B. So A.I.L has this type A.I.X. And then when it takes a step, it goes to B1.L, which has this type B1.X. So we would want to be able to relate these two types and say that, in effect, B.1.X is a subtype of A.I.X. But if you just look at the type definitions, this is not really possible, right? Because what you would need to do is, in order to show this subtyping relationship, you would really need to show that, well, on the right-hand side, you have this A.I.X, so you would have nothing here. And then on the left-hand side, you have this B.1, where all you know about B is that it's fully abstract, so you would have any. So you can't really show this in the abstract. And the only way you know that this might hold is because you know that there's a relationship between A.I and B.1. Namely, A.I is equal to B.1. And so, on the other hand, if I took a different if I took B2.L instead of B1.L, then clearly I wouldn't want to show any relationship here, because actually concretely A.I.X is a string and B2.L is an int. Okay. And so one more challenge is a subtyping transitivity. So the idea would be that if you have a chain of subtypes, so you say S is a subtype of T, and T is a subtype of type U, then you want this to mean in your system that S is also a subtype of U, and that's a very intuitive property that you would want. But then with path-dependent types, that really means that, okay, if you have a path-dependent type in the middle, then S, you've compared it with the lower bound of the path-dependent type, and you've compared it with the upper bound of the path-dependent type. So then the question is, what happens if you have a path with bad bounds? Should this even be allowed? And here is an example when you have P.L has like the very bad bound, so it has a lower bound of any and an upper bound of nothing. And then you would be able to prove that any type is a subtype of any other if you were able to use transitivity. So yeah, the question is, how do we deal with this? Do we try to avoid bad bounds from the beginning, or do we try to say, well, bad bounds can only happen when you have something that you would never be able to run in practice, so it doesn't matter, and that's one thing we have to consider. Okay, so just to recap, I wanted to go through one example that shows a bit all the features of path-dependent types and also some of the issues that can happen. All right, so here we have a trait animal which has an abstract type member food, and this method gets, which return food, and this method eats, which takes food. And so this is, gets is in a, since this is food is returned, it's in a covariant position, and here for eats, it's in a contravariant position. And then we have grass and meat, and cow is an animal which eats grass, and lion is an animal which eats meat. And incidentally, for cow, we also say that it's meat. Yeah, so then, okay, so then if we have Leo the lion and Milka the cow, then Leo can eat Milka. That's okay, because Leo eats meat, and here you can see that cow is also a subtype of meat. On the other hand, if you have an unknown animal, lambda, then it cannot, well, it cannot eat milka, right? Because abstractly, all we know is that it can eat this lambda.food, and we know nothing else about it. And here we just got milka as a cow, so we can't really subtype these things. And on the other hand, on the last line, you see that lambda.eats, it can eat what it gets, right? So that's good. That means that we are able to reason about these types abstractly without knowing concretely what they are. So here, for lambda.gets, we know that this returns lambda.food, and then lambda.eats accept lambda.food. So we were able to, even though we don't know much about the implementation of these types, we are still able to use them sometimes. And this relies on reflexivity, that lambda.food is a subtype of lambda.food. Okay. And what about sharing a byte? So if you have two animals, then they might want to share a byte. And here, for this to work in Scala, I'm using the with instead of the dot end, but the idea is the same. So here, if we have two lions, Simba and Leo, they can actually share a byte, and Leo.gets has this type Leo.food, and this is meat, and Simba.food is also meat, so that works. On the other hand, if Leo tries to share a byte with an unknown animal, it doesn't work because Leo.gets is expanded to meat, and then here we require something that both Leo can eat and lambda can eat. And since we don't know what lambda is, we can't really guarantee this statically. But the one thing that's interesting to point out is that if you have two unknown animals, well, you don't even know whether the type of byte here, you don't know even if that type makes sense until runtime. And by make sense, I mean, does it have, like, does all its type members have good bounds? So in the previous example, in the previous theory challenge, you saw that one challenge was, can we rule out bad bounds completely statically? And here the question is, well, in some cases we wouldn't even know statically whether a type has good bounds or not. And just to illustrate this, I'll show an example again. So here we have lambda 1 and lambda 2, and we say we cast them, we upcast them to be just animals, even though one is a lion and the other one is a cow. And now the question is, does lambda 1.food intersected with lambda 2.food, does it make sense as a type? So just to show that in some case it doesn't make sense, I'm adding this abstract type member T to food. And then for meat, I'm saying this T is nothing, and for grass, I'm saying this T is any, so that I can get into a situation that is where it would have bad bounds. So now statically, P.T is fully abstract. We don't know anything about it because we just lambda 1 and lambda 2 are both food, so we just know that we have this abstract type member T, but we don't know its bounds. And then at runtime, lambda 1.food is meat, and lambda 2.food is grass. So then if we try to look at P.T, then at runtime, its lower bound would be, so for the lower bound, what we do is that we take the union of the lower bounds. So in this case, we have nothing union any, and that's conceptually the same as any, because any is, like if you have something that is either nothing or any, then you know that it's any wins over. And similarly, for the upper bound, we take the intersection, and so nothing intersection any is nothing. So that means that at runtime, this P.T would have bad bounds. So now this is actually something concrete in our calculus where we see that we cannot rule bad bounds completely statically. All right, so with this, I want to conclude. So DOT is a core calculus for path-dependent types. And from a Scala point of view, one benefit would be to simplify the type system, to have a smaller core language, which would enable us to explain things better just in terms of these core constructs. And I showed you that it would enable better type inference through these classical intersection and union constructs. And hopefully the reasoning would be easier because there are fewer concepts to deal with. And I showed you some challenges in the meta theory. So type preservation is tricky because you have to take into account path equality. I showed you this example with inlining branding, which shows that while sometimes inlining seems to lose type information. And then path-dependent types with bad bounds. So the question is, what do we do with this? It shows up in subtyping transitivity, and if we admit subtyping transitivity and path-dependent types with bad bound, we kind of collapse or our types, right? And then so this I showed you that it's possible to get these runtime bad bounds via intersection types, even though statically you don't see them. All right, so I'll conclude here, and I'm happy to take questions. Thank you.
What happens with variance?
Yeah, that's a good question. So Martin in his keynote briefly mentioned it, but so the gist of the idea is that with variance, you have this, when you have this type member LM, you have a lower bound and an upper bound, right? And if you have something that's covariant, it means that you can always you can always make it more precise from above, right? And so what this means is that, say you would start with type LM is upper bounded by number, so you would just specify the upper bound as number, and you would leave the lower bound as nothing. So that means later you can say, well, the upper bound is actually integer, but that also means that if you try to use it in a covariant position, you wouldn't be able to, because when you in a contravariant position, you wouldn't be able to, because like this list.lm would be on the right, and that means you have to look at the lower bound. And since it's nothing, you wouldn't be able to actually use it. So there is a difference in terms of where these errors get detected with the compiler. So right now with these variants, you have these declaration site annotations, and here that would move the problem to use site. But this is almost like a question of the desugaring. So where do we report errors? But from a user point of view, you could still use these variants as you do now, and then you would at least have a conceptual understanding of what it desugars to, and that would allow you to reason also about what it means. Maybe hopefully in a simpler way.
But I wanted to point out that the advantage of this is that you don't have to declare variants for your generic types in advance, right? It means that and the way we currently do in Scala, you can simply analyze the use cases in contravariant or classify them into covariant or contravariant positions, and then see if whichever refinement you're trying to define makes sense. Another thing was, have you considered dealing with the subtyping challenges that you're facing by only analyzing subtyping relations between types that are concrete?
So yes to both of these things. For the first one, if you don't even use the type parameters, if you directly deal with type members, then yes, you have much more flexibility in defining what your variance means, right? I mean, you define your lower bound and your upper bound, and it can be anything between nothing and any, right? So you have a full range of things to consider. And yes, at that level, you would just have this use site declaration, but you control it fully, yeah. And for the second question, yes, so we've been trying a lot of things. And so the reason why just trying to deal with concrete things is hard is because you actually don't know until at runtime. It's basically the last example I showed. So there's basically you don't know whether a type is realizable or concrete until runtime. So for example, here this p, which is lambda1.food intersected with lambda2.food, it might make sense or not depending on what these two animals are, right? So it might have a concrete representation if lambda 1 was a lion and lambda 2 was a lion, then this type actually would make sense. And even abstractly, it makes sense because it just means that the type member T is fully abstract. But then for certain, when you know more information about what this lambda 1 and this lambda 2 is, suddenly you realize it doesn't make sense. So it's, I think there is more to explore there in terms of saying, okay, well, I'm in this context where I have these things that are impossible, so I know that at runtime I will never get there. But it's kind of tricky to always be consistent in what you allow and what you don't.
I have a question on this progress discussion on slide 19, I think it was. So, I mean, it looks to me if, like, the high string where you point out it's an error, but probably sound, I mean, if you expand the type on the right, then it's okay. So, you can't do that, or yeah.
Yeah, you're right. So it means that if you, the question is how much information do you have at runtime, right? Do you just know this trait abstractly, or do you actually know the actual runtime type? So you're right that, yeah, if you keep, yeah. So if you keep the fully runtime type, then maybe in this case you would be able to detect. But it's kind of strange, like statically, right? Because statically this is definitely not true, and somehow it happens during the runtime. Okay. Yeah.
Maybe I'll show. Okay. The Dotty compiler implements the dot calculus. So what does it do currently for subtyping?
Well, it uses subtyping constraints, right, and propagates them. But then, yeah, so there is there is still a bit of work to kind of merge the formalization with the implementation. So, but for example, this example we had earlier with something like this lazy val, that was actually a soundness issue in the compiler even when we showed this, because well, you have this lazy val and maybe you never actually implement it, but you use it as a type, right? So you use p.t, and this is completely erased later. So you can actually try to use this to collapse your lattice and maybe statically cast a string to an int, and then it doesn't at runtime. You never actually instantiate this piece, so you don't realize that it's unrealizable. So somehow, yeah, I mean the theory and the practice is kind of evolving together, and sometimes the theory helps find some issues in the practice.
Regarding the slide with the with the least upper bound computation, does the union type encoding allow us to get rid of the truncation of of the least upper bounds in Scala C, or is it just delaying the truncation until we actually need it?
Yeah, so you can think of it as delaying it one step at a time. So you would when you have this O, you would just say, well, it's C union D, and then when you need to look at the type T, where you can compute it one step and say, well, T is also probably C union D, and then every time you need to go one more step, you can actually do it.
I was using your desugaring also because so you said there are great benefits of using abstract type members over type parameters. So to also have this benefits, I was using this desugaring by hand, but the first thing I was running into is that you're cluttering the namespace, kind of. So the benefit of you having type parameters is that they're positional and you don't have members. How is this implemented in Dotty? So are you just mangling the names and putting indices there somewhere?
Yeah, that's a good point. So in Dotty, of course, it uses these private names, like with the dollars and everything. But there is also another tricky issue, which is if you're like inheriting from one of those positional type parameter class, then the question is, do you refine the same member, or do you create a new one? Or so there are a few issues there with. How do you deal with this proliferation of abstract type members when you do the desugaring?
Yeah. Did you consider interoperability with the Java type system yet? From practice, it's like it's always the worst part of the type system. So what's doing dot here?
Yeah, okay. In particular with union types, it might be pretty tricky sometimes. I mean, we're aware of this, but right now Dotty barely has a backend. So yeah, but it is something that will come up for sure. Like especially with union types, it might feel that some things would, if you wanted to actually implement them, you would need reflection to do them. But so this is something we would also need to consider, like restrictions in practice for Java. Okay, good. Well. Okay, so it's basically when you're using a method on union types, it figures out which case of the union you are at, and will use the members from this part using instance of checks. Yeah. Okay, cool. Thanks, Martin. All right. So, okay, I guess last question then.
So I was wondering, have you also tried to reduce the types the other way around, so from the modular to the function types? And I'm curious if that's feasible or not.
Yeah, so I think that might be harder because, like in some sense, with type members you have more power because you can refer to the member by name, right? And so, in particular, I was thinking, then you basically have this lambda.food that you can expect anywhere you want, right? So you do have more power from that because your names can escape the definition sites. So in particular, this example, like lambda.eats, lambda.gets, then here you can reason about it quite clearly by knowing, okay, it's lambda.food, and if you were using generics where you would have to know, okay, this is the same generic, but somehow, depending on where this is defined, you might sometimes need the name, I think. All right, I guess it's, it's already 10:50, so 10:52. Should we take one more question, or, okay.
With the path-dependent type encoding you're showing, will it be easier to encode virtual classes on top of that compared to Scala C, or is it probably just as hard as with the old type system?
Yeah, so I think you would still need some desugaring. I mean, one thing is that here in DOT, what I didn't mention is that we are mostly just thinking about the types and not so much about like the mechanisms for like inheritance and sharing code. So yeah, with just this base system, I think you can encode virtual classes, but probably it would also be, you would also need to like, yeah, the problem is with virtual classes, what you want is inherit this family of types, right? So you can do this, right? But it doesn't, the base calculus doesn't say anything about what implementations are inherited and things. So yeah, I think you could encode it. The question is whether intersections and unions makes it easier or not. I don't really think it makes much of a difference. All right, thank you everyone.